Alright, College Algebra, what we're going to be doing tonight is looking at section 2.6, graphs of basic functions. And the first thing we're going to look at is the definition of continuity. And then the reason this section is called graphs of basic functions is because we're going to be looking at 6 different basic functions and what their graphs look like. And these 6 different functions you're going to have in your memory for future reference and everything for the next section when we're going to be graphing these 6 basic functions and the way they can move around on the coordinate system. Okay, and then, so these are your 6 basic functions. The identity, a function that is being squared or cubed. So there's 3 of them. And then the square root, cube root function, there's another 2. And then the absolute value function. So altogether, that's 6. And then we're going to look at something called piecewise defined functions. And then, I don't believe we're going to do this one right here. That's not necessarily needed in this section. Let's go. So here's the definition of continuity. A function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. So if you lift the pencil from the paper at any point in time to draw your graph of your function, then it is not continuous. Otherwise, it's continuous. So this is, like it says, it's the informal definition. There is a more formal definition that if you're in my calculus class later, we will study. So it asks us in this first example, is all about continuity. It says, describe the interval of continuity for each function. Well, whenever we are describing the interval of continuity, we're going to state the interval of the domain over which is continuous. So for this first graph right here, looking at the domain, meaning the x values along the x-axis, starting going from left to right, we see that we can draw this graph from negative infinity to this point right here, because this right here is an open circle. That means it's discontinuous at that point. And also we are lifting our pencil to stop drawing at that point and then drawing the rest of the graph. So the way we're going to state this is, like I said, from negative infinity to that point on the graph that has the open circle, which is 0, if we're looking at the x values. Then we're going to put a parentheses around that 0 to show that it's not included in this graph. And then we're going to union it with the rest of the graph. So we begin back up at 0 and then go on drawing the rest of the graph, which goes on to infinity. So 0 again with the parentheses because it's not included in the domain, and then to positive infinity. And there, we're done. That's the description of the interval that is continuous. Now on this next graph, notice we draw this graph and we can do it without lifting a pencil. So if that's the case, then it is continuous over its whole domain, and that just means all real numbers, which in interval notation is negative infinity to infinity. Okay, so I hope that helps your understanding of what you're going to be doing in your homework. Here is our first of our basic functions. It is the graph of f of x, which is a linear function. And we just got done looking at linear functions, so y'all should know that linear functions also can look like this right here. I'm going to write out the function. F of x equals mx plus b, with m being the slope and b being the y-intercept. So that encompasses what any of your linear functions may look like that go along with graphing the identity function here. Okay, so this is what our basic function f of x equals x looks like. This right here, this, whoops, I didn't mean to draw that. This line right here is the identity function. And later on in the next section, like I said, I'm going to be using this right here to graph the rest of the types of linear functions that we come across. Alright, here is the squaring function. F of x equals x squared. So if you've been in my classes before in algebra, we have graphed functions that have x squared in it, and we found out that they look like those functions can look different when written out. So I'm going to show you another way that they can be written here. So x squared function can also be represented like this. This is also a squaring function with a, b, h, and k being just some real number, some constant. So next section we will be looking at graphing functions that have not necessarily all of these a, b, h, and k values within it, but in some way they will be there, and I will show you how to graph these types of functions. But know that this function right here that I just wrote out is going to have this shape right here, the parabola. Okay? Same goes with the cubing function. Whenever you see x cubed or anything cubed inside your function, the basic graph is going to look like this right here. And like the previous one, it can look like this right here. F of x equals some a times bx minus h cubed plus k. So again, our function will have this basic look of the graph, but can be rewritten in this form right here with a, b, h, and k being real numbers. Alright, the square root function. It always looks like this right here. And this is the way we're going to graph our functions. It has a beginning point, or it may even be the end point, depending on if it's not reflected over the x-axis or y-axis or not. And just like the previous functions, I'm going to write another way that it can look. It's always going to have those a, b, h, and k values in it. That's what I'm going to write. Okay, like I said, next section we will take a closer look at how the a, b, h, and k values change up the function in the way that it looks, but still it is going to have this basic look right here. It's going to have an endpoint, and then it's going to go on forever in one direction. The cube root function is similar to the square root function, except it's continuous over its whole x-axis here, and it doesn't have a beginning or end like the square root function. But here the cube root function has this basic graph, and I'm going to, again, write what we're going to be looking at in the next section here. So it's a cube root, that's a 3. Okay, so there is the cube root function. And lastly, we have the absolute value function, which again, the basic graph is always going to have this V shape. It can be upside down and be considered a function still, but not sideways. So this is the type of function we'll be graphing in the next section. And again, I'm going to write how it's going to look in the next section. So x is still inside that absolute value, just like the other functions. The x value is still inside the squaring function or the cubing or the square root and cube root. X is still inside that absolute value, so it's still going to have this basic shape right here that we are looking at for these basic graphs of functions. Okay, so that's our 6 basic functions and their graphs. So let's look at something else. We're going to look at how to graph what is called a piecewise defined function. In this right here, this function that I give you that has the equal sign and then the braces and 2 different functions within it, that is what we call a piecewise defined function. We are given the graph of 2x plus 4, and then again we're given another graph of x minus 4. And these piecewise defined functions can be broken down into as many functions as it wants, but it also tells you after the function where to graph it. And it says we only want this function graphed for this part of its domain. So for everywhere x is less than 1, we're going to graph at 2x plus 4. So I'm going to graph that part, and the way I'm going to start is by finding where the graph of 2x plus 4 ends, which is at 1. But remember also this is a less than symbol, and there's no equal to underneath it. So it's going to get an open circle whenever we draw this on our graph. But let's find the endpoint. If we plug in 1 for our x value here, we end up with 6. So on our graph, at the value of 6 on the y-axis, or sorry, not y-axis, on the y-axis, we are going to put at x equals 1, 6. We're going to draw that open circle, and that is where our 2x plus 4 part of the graph is going to end. And then also that's kind of where the x minus 4 is going to begin on part of another graph. So to get the rest of the graph, this is linear, we can look at that 2 is our slope, and we're just going to find another point using that slope. So 2 over 1, meaning rise over run. But on this graph, instead of rising and then rising and running like that, we're going to fall and then go to the left, because that is just the way we need to draw the rest of our graph. There is nothing after this endpoint right here for 2x plus 4. It's all in the negative direction. So fall down 2, go over 1. So fall down 2, go over 1. That's right here on the y-axis. I'm going to draw that point. And then connecting that circle and this point right here, that is going to be that part of the graph. Now, to get the other part of the graph, the 4 minus x, I'm going to find, again, its starting point. I'm going to find one of the points on that graph. So plugging in, again, 1, because that's where it begins on this graph, is at 1. I'm going to find that f of 1 for this portion of the graph. It has a y value of 3. So graph the point 1, 3. So 1, 3 is right here. And I'm actually going to put a closed circle on this one because it has that equal to symbol up here. And then I'm going to draw the rest of my 4 minus x graph similarly to the way I did the previous one. This has a negative 1 over 1 as its slope. So negative 1 over 1. Remember, you're going to go fall and to the right whenever you have a negative slope. So fall 1, go over 1. Your next point to your graph is going to be right there. And then it's going to keep on going, following that pattern. So connect the dots, and it keeps on going that direction. And there you go. We have graphed this function. And this is kind of how most piecewise defined functions are going to look like. They're going to be in pieces. Alright, so I'm going to show you one more example of a piecewise defined function. And notice this one, the pieces, this is a linear function, but this right here is a squaring function. And so the pieces of this graph are going to look quite a bit different. One's a line and one is a part of a squaring function. And remember, squaring functions have the parabola shape, and linear functions we know have the shape of a line. Anyway, to start us out, just like the last one, we're going to find for each piece of this function its ending or beginning point. And by plugging in 0 for each piece. So f of 0 for this first part of the function is negative 2. And then the second piece of the function, if we plug in 0, we get, again, negative 2. So they begin and end at the same point. 0, negative 2. And I'm going to put a filled in circle right here because of this part of my function right here says that x is less than or equal to 0. And since they have the same endpoint on the graph, this right here, the equal to symbol, kind of overrides the one that doesn't have an equal to on it. All right, so let's find another point on our graph for the linear part of the function. And we can just do that actually similar to the previous one, but we can also just find another x value that is less than 0. So pick a value that is less than 0 and plot that one and draw a linear function and draw the rest of the linear function. So that's what I'm going to do. I'm going to say, well, -2 is less than 0. So plug that in. And we get -2 minus 2. Well, that right there is 0. So plot the point -2, 0, because that's what this means. My x value is -2. My y value is 0. -2, 0 is right here. So connecting these 2 points, we end up having this portion of our graph. And then to get the second part of our graph, we're going to use the second part of this function, the x squared minus 2. And again, I'm just going to say let's find a point on its piece of the graph by plugging in a value that is greater than 0. Instead of less than 0, it's going to be greater. Because the rest of the graph, like I said before, it's going to be greater than 0. So let's plug in 2. And we're going to plug in 2 for our x value. Square it, subtract 2, which equals 4 minus 2. That's 2. So another point on our graph is going to be this x and that y, 2, 2. Here's another point on our graph. And remember, a squaring function has this u, this parabola shape, but for this part of the graph, it's just going to have this half of it, this piece of it. So with that point, just sketch out what the rest of the graph is going to look like, which is that there. That is all we have. That's our piecewise defined functions that you will be graphing in your homework, and also all the other basic graphs that we looked at. You'll have some stuff in your homework about it, and like I said, in the next section we'll be getting more into all of those basic graphs. So everyone have a good day or night, and I'll see you in class. Goodbye.